Everyone. It's my pleasure to introduce Prashanth Sridhar, University of Kansas, who will be telling us about finding maximal Cohen Macaulay and reflexive modules.
Thank you for the introduction. Before I begin, I'd like to thank Professors Eloisa Grifo and Sean Shet, the RAG staff, for this wonderful opportunity to speak. I'd also like to thank my PhD advisor, Professor Daniel Katz, and Professor Hailong Dao for their support through the course of this work. So the title of my talk, as you already saw, is Finding Maximal Cohen Macaulay and Reflexive Modules. So I'd like to organize the talk as follows, thinking of it as three segments. So the first one is basically why this study at all. And the second one and the third one are more specific scenarios in which I'll try to answer these questions. The first one concerning the existence of maximal Cohen Macaulay modules in certain settings in mixed characteristic, and the final one regarding reflexivity in dimension 1 or non-Gornstein rings. Okay, so I'm going to start with the definition of a maximal Cohen Macaulay module. So we have a local ring, and throughout this talk, it's going to be Noetherian rings and finitely generated modules over it. So a maximal Cohen Macaulay module or a local ring. So a non-zero R module is a maximal Cohen Macaulay module if it's finitely generated, and every or equivalently some system of parameters of R is a regular sequence on this module. It's also known as a small Cohen Macaulay module. So the thing to note is that even a non-Cohen Macaulay ring can admit a maximal Cohen Macaulay module. So in that case, it's an object that in some sense has better properties than the ring itself. And sometimes the existence of such an object can actually tell us something about the ring itself. So the properties of these modules have been studied extensively, of course. And likewise, another very classical object is a reflexive module, studied extensively in commutative algebra and algebraic geometry. So the definition is as follows. We have a Noetherian ring. M is a non-zero R module. Then M is reflexive if this natural map from M to its double dual is an isomorphism. So here the M star denotes the dual module, set of maps from M to R, module of maps. And in fact, it's true for finitely generated modules or a Noetherian ring that any isomorphism is sufficient. We don't actually need the canonical map. If we have some isomorphism between M and M double star, it actually implies that the canonical map is an isomorphism, but we need M to be finitely generated for it. Okay, so are these related in any way? There are some relations, but it doesn't go too far. So for example, in low dimensions to dimension 2, reflexive implies maximal Cohen Macaulay or Cohen Macaulay rings. And going the other way, in arbitrary dimension, if it's a normal ring, Gornstein ring, maximal Cohen Macaulay implies reflexive. So, but they're certainly pretty different. And examples are pretty easy to come by, actually. So let me give one example here. So if you pick a one-dimensional Cohen Macaulay local ring, let's say it has a canonical module, let's call it omega, then the ring is Gornstein if and only if omega is reflexive. So if you take a one-dimensional Cohen Macaulay local ring that's not Gornstein, then the canonical module is maximal Cohen Macaulay but not reflexive. And the other example is easier. Just take any non-Cohen Macaulay ring, it's reflexive, but it's as a modular itself, it's obviously not maximal Cohen Macaulay. Okay. So properties of these objects have been studied quite extensively, but the questions that we're going to concern ourselves are fundamental regarding their existence. So how do we find these objects? And if they exist, are they ubiquitous or maybe not? And if they exist, are there finitely many of them in some sense, and how to construct them? This has been the theme of what I've been doing during my PhD, roughly speaking. So let me begin with the second segment, where I talk a little bit about maximal Cohen Macaulay modules, then I'll move on to reflexive modules. Okay. So Hochster conjectured that every complete local domain admits a maximal, or otherwise known as a small Cohen Macaulay module. So this is clearly true if dimension is at most 2. For example, if the ring is dimension 1, domain is automatically Cohen Macaulay. If it's dimension 2, we can take its integral closure because it's complete. That works. And then there are examples of non-catenary rings that do not admit a MCM module. So to avoid these pathologies, we have this complete hypothesis here. And there's also results such as this one due to MJ Burton, where we have a non-Cohen Macaulay UFD. So it's a nice non-Cohen Macaulay ring, but it does not admit a MCM module of rank 1. So there are some rank constraints available. Primarily, this was interesting because it implied many of the other homological conjectures, which are, of course, now theorems, and in particular, the positivity of Serre's intersection multiplicity conjecture. Okay. So this conjecture is known to be true only in very few cases, and in general has been a difficult question to answer. So let me give a couple of examples. So this one is independently owed to Hartshorne, Hochster, and Peshkin-Shapiro. So any three-dimensional n-graded domain of positive characteristic P admits a maximal Cohen Macaulay module. And more recently, Schouten showed the following, that any three-dimensional pseudo-graded local ring of characteristic P admits a maximal Cohen Macaulay module. And there are also some other results over dimension 3 local rings of characteristic P due to Haynes and Schauten's. But in different characteristics and higher dimensions, the results are pretty much scattered and only a handful of them are known. So let's look at this problem from this angle. So we can reduce this problem to the integral closure of a complete regular local ring in a finite Galois extension of its fraction field. So it makes sense to start looking at nice Galois groups to begin with. So Roberts has the following theorem. So S is a regular local ring, L is its quotient field, K is a finite abelian extension of L. Let's say the Galois group is G. And critically, the order of G is not divisible by the characteristic of the residue field of S. Then in that case, the integral closure itself is Cohen Macaulay. So in particular, this applies to the equal characteristic 0 case. So in this case, it's all well and good. So even though this doesn't apply to the characteristic P case, it can be shown using elementary Galois theory that even the conclusion holds in characteristic P as well. But however, it fails, unfortunately, in the mixed characteristic case. And it fails quite badly, as we shall see. So we shall call this case the modular case, just for easy reference. That is when the degree of the extension is divisible by the characteristic of the residue field. Okay. And so the primary reason Roberts' argument works, it hinges on a nice decomposition of the group algebra Kg. So here the small k is the residue field and G is the Galois group. So this Kg splits as a product of fields in the case of Roberts' theorem. But on the other hand, let us look at a case when K over L is a cyclic extension of degree P. Suppose the characteristic of K is P. Then Kg looks like that. And that certainly is not a product of fields. So we run into trouble here. Okay. Here I would also like to note that Roberts' theorem goes through if S is only assumed to be a UFD. So in that case, the integral closure is a free S module. But Hochster and Roberts give an example of a local UFD S of mixed characteristic 2, such that its integral closure in a quadratic abelian extension of its quotient field does not admit any non-zero S-free module. So what this shows at least is that the argument verbatim does not go through in mixed characteristic, but it doesn't disprove the small Cohen Macaulay module conjecture either. So, and also Roberts showed that his theorem is false if G is only assumed to be solvable or nilpotent, so abelian is required. In fact, he shows the following. He shows there are Galois extensions of degree 8 of a characteristic 0 regular local ring S such that the minimal number of generators of the integral closure R over S is arbitrarily large. So the degree of extension is fixed, but the number of generators can be arbitrarily large. So one of the directions in which I've been thinking is there any correlation at all between the possible representations of this Galois group and the depth or SN bounds for the integral closure R? Are these two things correlated at all? But let me first fix a setting so that I'll be able to describe this rigorously. So primarily, I've been looking at extensions of the fraction field of an unramified regular local ring S with the following property. The integral closure is in an extension is already free if S happens to contain a field, but not necessarily so in the mixed characteristic scenario. So for example, the abelian extension case we saw. So the motivating factor for my thesis and also for my present joint work with Professor Katz is developing some kind of a mixed characteristic analog of Roberts' theorem and study the obstructions one faces when P divides the degree of the extension with a twofold objective, determining when the integral closure is Cohen Macaulay, and also find bounds on the depth if that's feasible. And when it is not Cohen Macaulay, determining whether it admits a maximal Cohen Macaulay module. Okay, so where do we start here towards this objective? Radical extensions seem to be key, apart from being good examples of this phenomenon. So here, by radical extensions, I mean there are joining nth roots to that regular local ring, and P divides that n. So the reason why radical extensions are also important is that Kummer theory implies that given an abelian extension K over L with Galois group G, if we have some suitable roots of unity, then an abelian extension is essentially a repeated radical extension. So in some sense, these are building blocks of abelian extensions in some scenarios. Also, it follows from a paper of Huneke and Katz that when S has equicharacteristic 0 or mixed characteristic Q different from, Q does not divide N, then in that case, the integral closure of S in some radical tower of nth roots is actually Cohen Macaulay, as long as we allow some reasonable generality hypothesis. So this is only interesting if that Q actually divides that N. And in general, we're only going to consider square-free radical towers. What I exactly mean by that is that the elements whose roots we adjoin are going to be assumed to be square-free. Because you can always reduce to this case if you're worried about finding a maximal Cohen Macaulay modulo or the integral closure. We can preserve finiteness and reduce to this case. So all the elements whose roots we adjoin are going to be square-free. So the first known example of the failure of Roberts' theorem was by Coe. This was around in late 80s. And he gave an example of an abelian extension K over L of a ramified regular local ring S of mixed characteristic P with field of fractions L, such that the integral closure is not Cohen Macaulay. In the late 90s, Katz gave an example of a pth root extension of an unramified regular local ring, such that the integral closure is not Cohen Macaulay. So this one is unramified. Both the examples were obtained by adjoining a pth root of a non-square free element. So they were radical extensions. But however, Katz showed that in case we adjoin the pth root of a single square free element, the integral closure is actually Cohen Macaulay. So we might think that maybe if you just adjoin square free elements, it always stays Cohen Macaulay and hope for something nice, but unfortunately that's not true. The integral closure need not be Cohen Macaulay in a finite square free tower of pth roots. In fact, it fails even if you adjoin just pth roots of two square free elements. So it could fail. So the motivating question for this next part of the talk is, does the integral closure of a regular local ring of mixed characteristic P in a finite abelian extension of its fraction field admit a maximal Cohen Macaulay module? So towards this, Katz answered this in the affirmative in a certain setting. So suppose we take an extension by a pth root of an arbitrary element of S, then yes, it does admit a maximal Cohen Macaulay module. And in fact, it's a birational one, so it's rank 1. So it feels like it could be true at least when the Galois group is cyclic, but that's yet to be determined. However, if we start looking at square-free towers, like we have multiple roots, the complexity seems to increase pretty fast. So to get an intuition for what happens in these towers, I carried out a careful study of biradical extensions of an unramified regular local ring S of mixed characteristic P, where we adjoin pth roots of sufficiently general square-free elements, say Fg from S. So one may think of this as the case where the Galois group is product of 2 copies of Zp. Okay, so let me set up some minimal amount of notation so that I'm able to state the results that follow. So S is just going to mean an unramified regular local ring, mixed characteristic P. L is going to be its field of fractions, and the dimension is at least 3. So this F and G are going to be some random elements from the maximal ideal, square free, relatively prime, or could be that they're units. They're not such that they're not pth powers in the ring. So the capital F and capital G are just going to be those polynomials, monic irreducible, and K is going to be that extension by pth roots, omega and mu of F and G. And R is going to be our object of interest, the integral closure of S in K, which is the integral closure of this ring A, where we adjoin omega and mu to S. So A is actually a complete intersection. It's just this regular local ring modulo these polynomials. And SP is going to denote the subring of S that's obtained by lifting the image of the Frobenius map on this factor ring back to S. And this symbol here, maybe I should find a better notation for it, but it's a multiplicative subset of S of elements expressible in this form. Okay. So the first observation we see is that if we invert P, suppose we invert the integer P, then it's essentially like Roberts' theorem, and that's integrally closed and it's Cohen Macaulay. So what this tells immediately that in the ring A, every height 1 prime that does not contain the integer P is already regular. And moreover, it's better because there exists just one height 1 prime, let's call it capital P, that contains this integer P. Okay, so kickstart the study of biradical extensions, there are some easy cases that we can knock out of the way. For example, if F is not in SP, one of them is in SP, or if one of them is divisible by P, then R is actually Cohen Macaulay. So there are a lot of combinations one could work with, but it kind of gets complicated. So we can avoid this situation by doing the following. So if S is a complete unramified regular local ring of mixed characteristic P with a perfect residue field, then there exists a finite extension of unramified regular local rings such that this S sits inside TP. So it goes and sits inside this subring of T. So why does this help? Because this allows us to assume that the elements whose roots we adjoin are in SP. So if you want to find a small Cohen Macaulay module over the integral closure, we just want to look at this case. So why does this work? Let me quickly say something about it. So here is our S and the R and the K that we're interested in. And this extension T, suppose its fraction field is K prime. And we simply take the join of those two fields and take the integral closure up here, let's call, say, script R, suffices to find a maximal Cohen Macaulay module over script R. But then this extension K prime to kappa is also a biradical extension. And then those roots start to lie in TP. So essentially, we can start over and assume that in the first place, it was in SP. So the advantage of one of the advantages of this is that it gives us a better handle on the integral closure, easier computations or easier descriptions of the integral closure, and hence easier ways to find the maximal Cohen module. Okay. So I'm just going to assume that f and g are in SP and fg are not divisible by p. And so H1 and H2 are going to represent pth roots of f and g modulo p respectively. All right. So the first observation we have is was actually surprising when first saw this. So the integral closure is actually Cohen Macaulay if one of these pieces is not integrally closed. It's kind of counterintuitive, but the reason is roughly that when these are integrally closed, the integer p gets ramified here in these rings, and it kind of gets trapped in a lot of relations. But in this case, there is an unramified branch, so as to speak, that is basically an unramified extension of one-dimensional domains, where here we're localizing at that principal prime p. So that automatically says that the non-Cohen Macaulay cases are going to occur when both of these are actually integrally closed. So let's move on to that case. And in that case, we see when both of these are integrally closed and this weird condition holds, R is Cohen Macaulay. But let me explain what that condition means on the next slide. But for now, if p minus one of these relations hold, then R is actually Cohen Macaulay. And in this case, the conductor is the p minus first symbolic power of p, where here the capital P is that unique height one prime that contains small p. So what is this condition? So this condition is saying that some subring here is normal, basically. For example, if P is 2, it's saying that S adjoint omega mu is integrally closed. If P is 3, it says both of these rings are integrally closed, and so on. And the powers of the prime we saw are not P primary in general in this case. However, the P minus first symbolic power is Cohen Macaulay, and it has a pretty simple description. We just have to throw in the integer small p. Okay. So I'm first going to tell a little bit about mixed characteristic 2. This is because the results here are a little sharper, because in this case, the extensions are automatically abelian, so there is some more legroom here. For odd primes p, if we allow a primitive pth root of unity in this S, it actually ramifies p. So it's a little, the results there are a little less sharp. Okay. So we have an unramified regular local ring of mixed characteristic 2. Both of these are integrally closed, and we have such a relation. Basically, it doesn't satisfy the hypothesis of the previous theorem. And what this says is that R satisfies this isomorphism as S modules. So there is this factor here, which kind of potentially could make R not Cohen Macaulay. And so this Q is basically this 3-generated ideal where H1 and H2 are pth roots of f and g modulo p. So this implies two things. Firstly, that R need not be Cohen Macaulay. And secondly, that the depth is at least d minus 1. So there seems to be a lower bound at least here. But if f or g is a unit, R is actually Cohen Macaulay. And in summary, it's saying that R is Cohen Macaulay if and only if this ideal is a grade 2 perfect ideal. Okay. So to summarize the picture in mixed characteristic 2 at least, suppose we assume f and g are in S2, then this characterizes when R is Cohen Macaulay. So one of these things must happen, which you already saw. But the point is that the second point says that if R is not Cohen Macaulay, R admits a birational maximal Cohen Macaulay module. So I also quickly describe what that module is. It's pretty simple. So if J is the conductor of R to A, that's an ideal in A, and P is the unique height one prime that contains small p, then JP star is the MCM module over R. So that's the module I'm referring to in point 2. Okay. So as a corollary of this, if we allow S to be complete and also the residue field to be perfect, then we can do away with the assumption that FG is in S2. And we also need to allow an extension of the quotient field And so in this case, doesn't need to be in S2, then R simply admits a maximal Cohen Macaulay module. Okay. So in mixed characteristic 3 and higher, it's pretty similar. Let me summarize this here. So the first one just gives some sufficient conditions for R to be Cohen Macaulay, which we already saw. The second point here is basically indicating that R need not be Cohen Macaulay. That's the point of having part 2. So if there are 2 of these rings are integrally closed and we allow such a relation, and note here that the index is just 1. There's a similar thing for higher indexes, but it just gets a little messier, so I didn't include it. And so in this case, R is Cohen Macaulay if and only if Q is a grade 2 perfect ideal. But also, we see that the projective dimension is pretty low. And also the number of generators of R over S is less than equal to P squared plus 1. Its rank is P squared. So it's generated by 1 more than the bounded above by that. And if F or G is a unit, then R is Cohen Macaulay. So in particular, if R is not Cohen Macaulay, and here I have an extra assumption here that Q has grade 3. So this is a regular sequence. Then R admits a birational maximal Cohen Macaulay module. In case Q does not have grade 3, R certainly need not be Cohen Macaulay, but at this point, I do not know how to do it birationally, but I can do it in certain cases by expanding the quotient field. It also appears that R is not too far from being Cohen Macaulay, in the sense that the depth is at least d minus 1, and it can be generated by 1 more than the rank number of elements. So it seems like there could be something nice going on, but it's actually deceptive because if, suppose the dimension is at least 3, it could be that R does not even satisfy S3. So there is no non-trivial lower bound on N where R satisfies Sn. It has to at least satisfy S2, but there is no lower bound. It need not even satisfy S3. Okay, so the techniques are pretty well known. So here, the first one is studying the structure of the conductor J of the integral closure R to A. And since A is Gornstein and J is unmixed, R is Cohen Macaulay if and only if this ring is Cohen Macaulay. So we can use this to tell when R is Cohen Macaulay. And to show that it admits a birational maximal Cohen Macaulay module, we can choose a suitable ideal I, depends on the circumstance, of course, such that I star is a J star module and the depth is the correct one. Okay. So one consequence of this study is that we can generate examples of non-Cohen Macaulay R relatively easily. So it gives a collection of examples for which I'm trying to compute numerical invariance in hopes to see if there are counterexamples for certain questions in the literature. And let me write down one example here. So for example, this is a 3-dimensional ring. Suppose we take F to be so, G to be so. F, G are actually in SP. And the H1 is x squared, H2 is xy. F, G are actually square free and relatively prime. And this gives rise to an example where Q has grade 2, but projective dimension is 3, and hence R is not Cohen Macaulay. But it can be shown that, at least in the case of this example, that R admits a maximal Cohen Macaulay module. Okay. So at this point, let me talk a little bit about small Cohen Macaulay algebras, which are essentially, we can think of it as small Cohen Macaulay modules, but they have a ring structure to them. So we came across this first when I was looking at this biradical case, saw that when F and G both do not belong to SP, R is not necessarily Cohen Macaulay. So this was the example that I constructed, was a 4-dimensional ring here, and F and G are so, and they're square free, and they form a regular sequence in S and do not lie in S2. It can be shown that R is Cohen Macaulay if and only if this ring here is Cohen Macaulay, using what we saw earlier. and that the latter is actually not Cohen Macaulay. It's not too hard to see. But however, what is interesting is that the integral closure of R adjoint square root X is a Cohen Macaulay ring. So it's a small Cohen Macaulay algebra for R. So this has to be contrasted with the fact that in equal characteristic 0, small Cohen Macaulay algebras do not exist for normal non-Cohen Macaulay rings due to a simple abstraction from the trace map. But as we just saw, they can very well exist in mixed characteristic. And but on the other hand, they need not exist always as well. Bhargav gave examples of non-existence of small CM algebras in positive characteristic. And upon discussion with Professor Linchuan Ma, we saw that these examples actually can be deformed to mixed characteristic. So that means that it need not exist always. However, let us consider the following situation. So we have an unramified regular local ring, mixed characteristic P, fraction field L, and we have some finitely many elements here that lie in S P wedge P squared. So they're P powers modulo P squared. They're square free and mutually coprime. So we are joining nth roots of these things, and such that P divides this order, but P squared does not. And there is this exceptional condition that if Fi is P itself, then we need to assume that Ni is exactly P. So we can think of this as Pth root tower of elements from P wedge P squared. Then the integral closure is actually Cohen Macaulay. So what this does is that this enables the existence of small CM algebras for a broad class of non-CM rings. So there are a lot of non-CM rings sitting inside this, and such an construction enables existence of a small CM algebra. So one general approach that we have taken is when S is complete with perfect residue field, we kind of reduce to this SP case and then ramify the integer P suitably and try to expect some behavior that is similar to theorem 16. Okay, so let me end the second segment by just summarizing the motivating questions one more time. So here our standard setup. The question is, if K over L is abelian, does R admit a maximal Cohen Macaulay module or algebra? So Professor Katz and I are working on this presently, and there are some partial answers, but nothing complete yet. And we could make a reduction to the p torsion part of the abelian group under one exception. So it looks promising, but obviously the harder part is the p torsion. So and then if R admits a birational or maximal Cohen Macaulay module, can it admit a small CM algebra? So the intuition here being if it admits a birational MCM, then roughly speaking, the relation, the bad relation is killed by something non-integral. And so in that case, does it somehow obstruct the existence of a small CM algebra? Roughly speaking. At this point, I would like to switch over to the other classical object, reflexive modules, and talk a little bit about it. So for nice rings, for S2 rings, reflexivity is essentially a dimension 1 problem. So a reflexive module over S2 ring is basically an S2 module that's reflexive in codimension 1. So for example, over S2 ring, maximal Cohen Macaulay modules being reflexive is actually a dimension 1 question. And some general facts are known. For example, if R is reduced, any second syzygy or dual module is reflexive. But reflexive modules or even ideals are not well understood, even in the case of a one-dimensional Cohen Macaulay ring that is not Gornstein. Questions such as, so ref R here refers to the category of reflexive R modules. When is it finite in some sense? How many can there be? Can we classify them? Based on the study of reflexive R modules, can we say how far the ring is from being Gornstein, and so on. So all of what follows is joint work with Hailong Dao and Sarasij Maitra. So our setting is going to be that of a one-dimensional, analytically unramified Cohen Macaulay local ring. Typically not going to be Gornstein, because if it were, it's the same category as MCM modules, and that's already well understood. Okay, so analytically unramified because if the integral closure were not finitely generated, then, for example, the category of reflexive R modules is always of infinite type. It needs some proof, but it's not hard to see. So we typically restrict to this case. Okay. So let me start by saying this. The nicest modules are free R modules, and they are always reflexive. And reflexive in this setting implies maximal Cohen Macaulay. So CM here is MCM here. And R is regular if we have equality throughout. And R is Gornstein if we have equality in the second inclusion. So we are basically going to study ref R in the cases when R is really close to being regular or Gornstein, and try to understand those cases first and then move on to the harder ones. Okay, so the techniques include so-called Ionrich modules, properties of conductors of birational extensions, colength of the conductor ideal, and trace ideals. So let me define what is an Ionrich module. It is a straight generalization of what an Ulrich module, but let me say why this definition was introduced in the first place after I define it. So for a maximal Cohen Macaulay module M, it is I Ulrich if for a regular ideal I, the Hilbert-Samuel multiplicity of I on M is the length of M modulo Im. So this symbol here denotes the category of I Ulrich modules. Okay, so this is...
Right, what do you mean by a regular ideal? Do you mean that the...
It contains a non-zero divisor.
Okay, thanks.
Yeah, right. So, so in M Ulrich modules are basically the regular Ulrich modules, so the maximal ideal where M is the maximal ideal. So the reason why this was introduced is that this helps in tracking reflexivity in dimension 1. It's a good way to keep track. And so for a regular ideal I, suppose if you let P of I denote this so-called blow-up ring of I, it's the union of endomorphism rings of the powers of I. So in that case, if M is a maximal Cohen Macaulay R module, the following are equivalent. M is I Ulrich, this isomorphism is satisfied, and M is a maximal Cohen Macaulay B of I module. So we actually went from 2 to 1. While studying reflexivity, we saw that this kind of an isomorphism keeps showing up, the second one. And so we defined 1. So we went 2 to 1 in the natural direction. Okay. So for examples, if I is any regular ideal, the integral closure and the conductor are always I Ulrich. So if you have a finite birational extension S, then S is I Ulrich if and only if it happens to contain this B of I ring. And the relation to reflexivity. So what does it have to do reflexivity? The first link is that in nice cases, the canonical module can be identified with an ideal of the ring. So omega Ulrich modules, where omega is the canonical module, are reflexive. So for example, for large n, that means that the powers of this canonical ideal are always reflexive, because for large n, these are omega Ulrich. But it doesn't mean that omega is reflexive, because omega is reflexive only if the ring is Gornstein. So we can also look at maximal Cohen Macaulay modules or omega Ulrich extension. And maximal Cohen Macaulay modules over such an extension are going to be reflexive, as we shall see. Okay, so there are some nice algebraic properties that these modules satisfy. For example, if you home into a maximal Cohen Macaulay module, it stays I Ulrich. It has some nice behavior along short exact sequences, and so on. And moreover, these ideals, if you look at only I Ulrich ideals, they form a lattice in the sense that they're closed under intersections, additions, and the largest element is this ideal, small b of I, which is the conductor of capital B of I. And we have this following link with the core of the ideal I. And this essentially follows from a result of Pollini and Ulrich, which describes the core. So in this case, this equality holds, that is this B of I, the largest ideal is actually core I colon I. Okay. So a finite R algebra S is strongly reflexive over R if any maximal Cohen Macaulay module over it is reflexive. So for example, R is strongly reflexive over itself if and only if R is Gornstein. So the question is, can we characterize such extensions? But we might ask, why do we want to do this? The reason is that if this characterization is done in a computable manner, we can generate examples of reflexive modules, because it's easy to find modules over a ring, but then they're automatically reflexive. Moreover, if S is a strongly reflexive extension, it can be shown that if you start with a regular ideal and then take its closure in S, meaning that we expand it and then contract back, that's a reflexive ideal. So we can generate lots of examples from such extensions. So here is a characterization which is kind of computable. So we are in the setting of a one-dimensional Cohen Macaulay local ring. It has a canonical ideal omega R. So this canonical ideal is available, for example, if the ring is reduced, or if the ring is, more precisely, if the ring is generically Gornstein, meaning that localized at minimal primes, it's Gornstein. So if S is a finite extension of R, the following are equivalent. So any MCM module is reflexive, which is strongly reflexive. That was our definition. And this is simply equivalent to omega S being reflexive. That is the canonical module of S being reflexive as an R module. In fact, a little bit more is true, that this is the canonical module on the left-hand side here, Hom R S R. It's actually isomorphic to the homing into omega R. And it's equivalent to being omega Ulrich as an R module. So this is the computable part. So this kind of gives us ways to generate reflexive modules. And finally, for the last implication, we are assuming that S is a birational extension, because only then does the conductor make sense. So S is R reflexive, and the conductor of S to R lies inside this object, which is core omega colon omega, where omega is the canonical ideal. Okay, so one corollary of this is that if you take any extension of the total quotient ring of R and look at the integral closure there, and suppose the integral closure is a finite R module, then it's reflexive. So this is in dimension 1, but we can say something in arbitrary dimension as well. So this is a slightly technical one. It just says that if R is generically Gornstein, means that we need a canonical ideal in dimension 1, and it's an S2 ring, arbitrary dimension, and the algebra S is S1. If this extension is strongly reflexive in codimension 1, then any finite S2 module, S2S module, is actually a reflexive R module. So the point of this is to conclude the next one. That is, if we have a generically Gornstein S2 ring of arbitrary dimension, and we take an extension of the total quotient ring of R such that the integral closure of R in A is a finite R module, then it's reflexive. So this generalizes some results that are already known, for example, for normal rings, things like that. Okay. So let me, for the last part, talk a little bit about finiteness results. So we have a class of objects that is said to have finite type if there are only finitely many indecomposable objects up to isomorphism. So consider the following. We have a one-dimensional Cohen Macaulay local ring, infinite residue field. Then any reflexive regular ideal of R is isomorphic to some ideal containing the conductor C. So if one wants to study the category of reflexive ideals, then we can basically, study the finiteness of reflexive regular ideals. Then we can restrict to ideals that contain C. And based off this and what we discussed earlier, we have the following finiteness result. One-dimensional analytically unramified Cohen Macaulay local ring. C is its conductor ideal. So either K is infinite or this condition on the minimal primes. Then basically roughly what this says is that the conductor co-length is small, then ref1R is of finite type. So so this is conductor co-length being small can be seen as being close to regular, close to being integrally closed. Then ref1R is of finite type. But when the co-length is 4, we need R has minimal multiplicity. And certainly this is required because we found a counterexample that it fails. So suppose if R is this one-dimensional domain, it's a complete intersection, has multiplicity 4, and it's not minimal multiplicity, but the co-length is 4. But it can be shown that ref1R is not a finite type. So it fails in co-length 4 for the first time. Okay. And this one is basically a finiteness result for the category of reflexive modules, not just ref1R. So in this case, it's pretty much the same thing, just that it's reduced, but the conductor is actually equal to M. So it's pretty close to being regular. Then ref-R is of finite type. Okay, so we can say a little bit more in the case of almost Gornstein rings, which as the name suggests means that it's close to Gornstein rather than regular. And what this means is that formally it means the maximal ideal is omega Ulrich. So for Gornstein, the ring itself is omega Ulrich. Almost Gornstein, we can think of it as the next case where M is omega Ulrich. So for example, in such rings, all powers of trace ideals are reflexive. So what is a trace ideal? It's the trace ideal of an R module M is the image of this natural map from M star tensor M to R. Basically, it's the image of the ideal generated by image of all maps from module to R. And ideal I is a trace ideal if it's equal to its own trace. So examples would be just maximal ideal, the conductor, or the conductor for any finite birational extension S. So we show that general trace ideals need not be reflexive. An example didn't seem to be known in the literature. So that must be contrasted with the first result here, that all powers of trace ideals are reflexive, but in general, even trace ideals themselves need not be reflexive. And it's well known that the maximal ideal is reflexive, but we show that even M squared need not be reflexive, for example. And if you're hoping for something like all large powers are reflexive, even for the maximal ideal, that's not true. It could be that all large powers of M are not necessarily reflexive. Okay, the following question is a question from Faber. It asks that if R is a complete local or graded ring, are the following equivalent? CMR is of finite type, and there are only finitely many possibilities for trace of M, or in other words, only finitely many trace ideals. So in that case, the answer to this question is no, actually. And here's an example. So if you take this ring here, K is infinite, E at least 4, multiplicity is at least 4, then the set of trace ideals is finite, but CMR is infinite. This can be shown using what we discussed earlier. The trace number of trace ideals is actually just 2, the ring and the maximal ideal. So this kind of leads us to ask, can we classify what does it mean for a ring to have finitely many trace ideals? So we kind of do this for up to 3 trace ideals when R contains a field, but largely we didn't explore beyond that. So in general, the motivating questions are for a setting of a complete Cohen Macaulay local ring of dimension 1, can we classify when the category of reflexive ideals is of finite type? So what does that tell us about the ring? And can we classify when ref R is of finite type? If an ideal I is reflexive, is its trace reflexive? The reason why this third question is in there is because it implies many other related facts. that help us towards question 1 and 2. So I'd like to point out the references for this talk. So the first 4 here are, for the first part of the talk, the maximal Cohen Macaulay part. The last one is for the reflexive modules part, and it's available on archive. So thanks a lot for your time and patience.
Cool. Let's thank Prashanth.
Thank you.
Any questions?
I have one.
Go for it.
So for the examples of MCMs and MCM modules that computed in the first half,
Yeah.
Do you know what the trace ideals of those modules are, or the algebras?
So let me see. So the trace ideal is, I'm not 100% sure, but it's probably computable. I can, it's probably, that's something that I could do.
Cool. For
but I don't know at
context,
this point.
I'm interested because for big Cohen Macaulay modules and Cohen Macaulay modules in general, the trace ideals are connected to the singularities of the ring. So I'm real curious now that you have more examples what those trace ideals are.
Okay, I'll try to certainly think about this and get back to you.
Thanks.
Nice. Other questions? All right. Hearing none, let's thank Prashanth again.